So you can see that we have allocated the supports for all these shear walls. And then we can also look at the load combinations. So basically we have applied the loads on the slab as unity, and then we found how much load is transferred onto each beam. But we have to convert these unit loads to the actual loads. For that, we can define load combinations. And you can see the self weight of the slab. And I said, I have used a density of 24 kilonewtons per meter cubed. So self weight, if you look at the self weight is due to 175 millimeter slab. So 0.175 multiplied by 24 gives you 4.2. So this should be 4.2 modify. I have earlier considered slab thickness as 150, now it is 175. And you can also see that, in this lift core area, I am having a different slab thickness, that is 200 millimeters. So when you have different slab thickness, define a different unit load. When you have a different slab thickness, define a different unit load. So I'll also say slab finishes. You can see it's everywhere we have allocated 1 kilonewton per meter squared. Say when you allocate 0.5 kilonewtons per meter squared, it generally represents cement rendering of 25 millimeter thickness. The reason is density of cement rendering is about 20 kilonewtons per meter cubed. So when you have 25 millimeter thick rendering, then the corresponding load is 0.5 kilonewtons per meter squared. But these days, most of the floor finishes can be in the form of tiling and all that. So you have to add the weight of the tiles also. And so it's good to go for something like 0.75 kilonewtons per meter squared. But there's a chance that, if the floor is not properly laid, fully leveled, and then there can be slight variations in the minimum slab thickness that you use. And to allow for all that, sometimes it's possible to use a value of 1 kilonewton per meter squared as well. So I'm using a value of 1. And then services. And again, in this area, sometimes you might get more services because some service lines may be running through this. So here I have considered this weight of services as 0.5 kilonewtons per meter squared. Or 0.5 kilonewtons means 500 newtons per meter squared, or 50 kilograms per meter squared. And if you think the services can be more, you have to allocate a higher value, but this will be a very reasonable value. And then we can also look at partitions. And if you look at Eurocode, depending on the weight of partitions per linear meter, the lightweight partitions per linear meter, they give different values like 0.5, 0.8 and 1.2 kilonewtons per meter squared. So you can look at Eurocode, the initial one, part 1 dealing with loads, and you see that when you have lightweight partitions, they allow the lightweight partition load to be represented as a UDL on the slab. So the values are 0.8, 1.2, and there's another low value also like 0.5 kilonewtons per meter squared. So I have allocated 1 kilonewton per meter squared here. And so again, you can see I have not allocated any partition load weight for this area. So I have done this just to show you that, you know, in a building, you can have you can use different unit load values, and also different unit load values, and some areas that, you know, you don't have to add all the loads. You can have you have to add those loads only if they are applicable. So here you can see unit load 2, I'm not having any partition load because it's a passage where people are able to gather. So, and then we have to also look at the live loads. And I have considered the different live load for this area, that is 4. And all the other areas, I have considered the typical office flow live load, which is about 2.5 kilonewtons per meter squared. So that is the, so with those, we can actually convert the load on slabs to loads on beams, corresponding loads on beams. And because we have defined for a particular case, then when you want to consider different types of loads that will be acting, including the self-weight, you can define these as combinations. And these combinations will help you to increase the load to the level that you need from a unit load. So we start with the unit load and then we enhance it to the actual load condition. So now we have got all these loads applied, and then there's another parameter that we have to think about. And so these are the loads, but how about the mass of the structure? Can some of these permanent loads increase the mass of the structure? So say for example, when you have a rendering, cement rendering, it's everywhere. So it should be represented, its mass should be represented. So what we can do is, we can go here. I shouldn't have said cancel. I think we change one of these, didn't we? Modify. So we said it is 4.2. Modify. Okay. And now we'll go to the mass source. Now it says, you know, you can apply the mass in 3 different ways. One is, you know, you define the actual mass by defining the elements. So when you define a column, you are defining the mass of the column as well. When you are defining a slab with the mass, it's already automatically defined. And if there's any other mass, say for example a handrail that you have not modeled, then you can ask the program to get the weight of the handrail or the mass of the handrail from the additional masses you are adding. So that means, you know, instead of the handrail, now we will add the mass, because in the actual model we are not modeling the handrail. So, but still, you know, you can represent the mass of the handrail by allocating a certain mass to the certain mass to a joint. You can apply a certain mass to the joint and then define the mass. On the other hand, you can get it from loads, or you can get it from everything you are defining here. From elements, definitely it will come, because we have defined the actual size for columns, beams, slabs. So the program can calculate the mass. And if you are going to place any additional masses, those also can be considered. But you can see the weight of the finishers. We have not modeled. Finishers we have not modeled in the building. In our model, there's nothing called finishers. Finishers is only a load. So we have to now convert this load that we consider as finishers to the actual structure. So what we do is go there and go to this one and say dead weight is always there. So that is due to the beams, columns, steps, and shear walls that we have already defined. So we don't have to worry of anything because dead load automatically will be calculated by the program and its multiply is 1. Then we can also have additional masses on in the form of unit slab 1 and unit slab 2, and these can take account of any of the masses that will contribute as permanent loads. And one of the examples is finishers. Finishers will be there as a permanent load. So now what we can do is the weight of the finishers can be added. In addition to that, if you think when you are making the allowance for partitions, we are making higher allowance. But in reality, the actual weight could be lower. So if you have some idea about the actual weight of the structure, then again, you can allocate. So let's say, I have allocated 1 kilonewton per meter squared for the 1 kilonewton per meter squared in this area for the partitions. And I'll say that, the actual weight of the partitions will be only about 50% of that or 70% of that. So you have to come up with a number. So let's say 70% of that. And then you can also have finishers. The finishers also, we are allocating a value which is higher than the actual. Actual can be about 0.5 or 0.6 or 0.7, but we are allocating 1. So let's say, 70% of the finishers weight can be there. So 70% means 0.7. And then let's say we are going to have, so we say 0.7 and add it. And in addition to that, we might get services, let's say about 0.3 kilonewtons per meter squared. So you get 0.7 due to partitions, 0.3 due to services, 0.3 due to services, and 0.6 due to finishers. 0.6 due to finishers. So altogether you get 1.6. So what you do is you can multiply this by 1.6 kilonewtons per meter squared, and then you can apply it here. So what the program does is, when it calculates the mass, it will get the mass that is coming due to the self weight of the structure. And in addition to that, on the slabs, it can consider some additional mass, and the additional mass is equivalent to 1.6 kilonewtons per meter squared. 1.6 kilonewtons per meter squared. So you are asking the program to convert this to the corresponding mass and consider that it accepts this slab level. So that way you can actually get a better estimate of the natural period of vibration of the building, because now you are actually considering the mass of the structure with a reasonable accuracy. So that's another change or adjustment that you can make. So whatever the program you are using, try and understand how the mass has been defined, and based on that you have to come up with the proper method of allocating the mass. And in this particular case, I have used the actual elements with the mass plus And I have made some allowance for some additional permanent loads that could be there in the building. So that way I can get an accurate estimate of the natural period of vibration of the structure. Can you understand that? So when you have a structure, we have to define two parameters. One is the mass, the other one is the weight. Weight will finally result in bending moments and shear forces, whereas mass will be important. Whereas the mass will be important to determine the dynamic properties of the structure. So any questions on that?
Excuse me, sir.
Yeah.
Can I ask a question on load distribution?
Yes, no problem.
When we have cantilever slab panels, like 3 edges have beams and with a free end, what's the load distribution? How can we apply the loads transferred to the beams instead of 2000?
Yeah, actually, you can apply the load directly on the beam.
For other beams, sir.
Say we have a cantilever slab here.
Yeah.
So that cantilever slab, that all the load on by the cantilever slab will finally come onto this beam. So you can have an additional load on this beam due to the cantilever slab.
Okay, sir.
Right?
Yeah.
So cantilever slab, because it's a statically determinate structure, you can straight away determine the load transferred onto the beam. So if you know the load transferred onto the beam, apply it as a separate load. Say you can say cantilever. Cantilever, you can have a name like cantilever, right? And
Okay,
then
sir.
due to the cantilever, if the cantilever is only on this beam, then you will allocate the load called cantilever on this beam. And if you have another slab here, cantilever slab, then this will also be loaded. But
Sir.
if you look at any other beam, there's no load due to cantilever. So you, when you are creating the combination, you will add cantilever. Okay.
So, sir, is there any load coming to the spanning beams, like outer spanning beams?
Let's say if you have a cantilever here.
Yeah, sir.
So only this beam will be loaded.
Okay, sir. Okay.
And that will be the load due to the cantilever, right?
Okay, sir. Okay.
So
Thank
you can also have cantilever, the dead weight and cantilever live load if you want, right?
Okay,
if you
sir.
want the load separately, cantilever dead and cantilever live can be added separately. Okay.
Okay, sir. It's clear.
Yeah. Any other question? Because cantilever is a statically determinate component. So the final effect of cantilever is to add more load onto the particular beam that is supporting the cantilever. So in the model, you don't model the cantilever, you will simply model the load, right? Because cantilever is not going to give any stiffness to the beam. Is that right?
Yes, yeah.
Cantilever is not going to stiffen the beam. If a cantilever is going to stiffen the beam, then you have to consider it that way.
Okay, sir. Thank you, sir.
Any other question like that?
Excuse me, sir.
Yeah.
Can I ask a question regarding the boundary conditions? In this case, you use pin conditions. So how we can choose whether to use pin or fixed condition? Is there any method or something, sir?
No. I will explain it. That is at the foundation level. Is that right?
Okay, so okay.
Yeah.
Okay.
So foundation level. Now that will all depend on how you can design the foundation. Now let's say you can design the foundation only for axial load, right?
Okay.
In that case, you can consider that the load, the columns are only supported by pin connection.
Yes, sir. Yes.
Right?
Yeah.
But that will be stable only if there are many other columns, and also if there are shear walls, then it will be a fairly stiff and correct situation, right?
Okay. Okay.
But on the other hand, now if you are having some pile foundation where the piles are having, say, four piles per column, so any bending moment also can be resisted by the piles, group of piles, then no harm in considering that it's fixed at the ground,
Okay,
right?
sir. Okay. Yeah.
So that will all depend on the type of foundation you are having. And let's say you are having an inverted T-type foundation, shallow foundation,
Yeah.
but inverted T-type, which is with say 1.2 or 1.5 meter deep beams
Okay.
running in one direction, right?
Okay, sir.
So in that direction, this inverted T also can resist some moment,
Yeah.
right?
Yeah. Yeah. Yes.
And if you have inverted T in the other direction also, then you can simply say the foundations are fixed.
Okay, sir. Okay. Yeah.
But otherwise, say, there's another method. That is, you will model the foundation and then model the springs. Model the foundation, the soil with springs.
Oh, okay.
And that way, you are not saying foundation is fixed or anything. You are just connecting it to the foundation. Because foundation is modeled with the springs, the actual behavior, reasonably accurate behavior can be obtained.
Okay, sir. Okay.
Right? So there are different methods, but there isn't a rule to say you must fix it. But only thing is, if you have considered that the column is fixed at the ground level, then there will be a bending moment transferred onto the foundation, and foundation should be designed to carry that bending moment,
Oh, okay, sir. So
right?
it means the design have the freedom to choose
Yes,
whether.
yes. Designer has the freedom, but designer has to make sure if he has assumed the fixed condition, then it is the loads due to that condition can be resisted by the foundation,
Okay, sir. Okay.
right? Okay.
Okay, sir. Thank you, sir.
Any other question like that? Any other question? Right. So then we'll move on to the other load combinations. So once you have these basic combinations, we discussed earlier, the first combination case 1 is the dead load 1.0 GK plus 1.5 WK, 1.5 WK. So here you can see wind load in x direction, linear add. So you have the self weight of the structure, that is dead weight. Now, although we have modeled the slabs, we have made them weightless. So that means there's no weight from the slab. So which means then you have to actually consider the self weight of the slab, right? All this dead load will not cover the self weight of the slab. The reason is we have considered that the density of the material of the slab is almost zero. That is to make sure that the slab loads are not transferred directly. The reason is if you consider this slab, you can see we are defined one element. So you can see the whole slab is modeled by one element. So the load transfer will be only to these four nodes, which is not an accurate representation of the load transfer. So that's why we are not considering that this element as weightless, and we are actually adopting the weight of the slab separately. So when you look at the load combination, you can clearly see that load combination 1 in x direction. Here you can see dead self weight of the slab, then finishers, services, partitions. So this is 1.0 GK plus 1.5 WK, and that is 1.5 times wind load. So when you have the wind load in X direction, then the wind can reverse and act in the reverse direction. So to take account of that, here you can see the wind load is appearing, but the scale factor is minus 1.5. That means we are reversing the wind, whereas all the other things remain the same. So similarly, you have to do this for Y and YY direction. And when you look at combination 2, you can see dead, self-weight, all are 1.5 factor. And then slab live is should be 0.7 times. Slab live should be 0.7 times 1.5, because we can have only one variable, dominant variable. So 1.5 into 0.7 is 1.05. And then when you allocate the live loads, you have to be mindful about this. Say, when you have a hole without, say, seating, generally, we can consider designing it for a load of 5 kilonewtons per meter square. You can think of designing it for a load of 5 kilonewtons per meter square. The reason is, if you have a lot of people gathered, then you will find that the actual load is about 2.5 kilonewtons per meter squared. That means, almost a lot of people gathered on a slab, almost standing next to each other. Then the corresponding load is about 2.5 kilonewtons per meter squared, or 2000 or 250 kilograms per meter square. 250 kilograms per meter square. So that's a kind of maximum load you can get on a 1 square meter area, because you cannot pack too many people into that area. So the actual crowd loading is about 2.5 kilonewtons per meter square. But when you are designing, we design for something like 5 kilonewtons per meter square. And that is to allow for any activity like dancing that can generate vibrations to happen on the floor that you have already designed for crowd loading. So crowd loading, actual load is about 2.5. But when you have various activities like dancing, then you allocate an additional load. So we say the actual load is 5 kilonewtons per meter squared for design purposes, but in reality, the slab need to be loaded only by 2.5 kilonewtons per meter squared. So in British codes as well as Euro codes, if you look at the Euro code national annexure for England, they allow this additional component to be reduced when you are looking at the overall loads acting on the structure. So when you are considering the overall effects, then there's no chance that every floor in the building can be used as a dancing floor or something like that. So because of that reason, you can actually go for something like a reduction like 50% when you have more than 10 floors identical in a building, and when you have less than 10 floors but more than 6 floors or more but less than 10, then you can have a reduction equal to 60% of the live load. And if you have only about say 1 floor, no reduction, 2 floors also generally no reduction. If you have 3 floors, you can have a reduction of about 10%. So that way, gradually we increase the reduction, And if it is 6 floors, we can go for 60%. 7, 8, 9, all 60% reduction. Whereas when you have more than 10 floors, we can go for 50% reduction. So that's why you can see here there's a mistake. That is, 1.5 into 0.7 is 1.05 divided by 2 is 525. So this has to be 0.525. So here you can see you'd expect this to be 1.5 into 0.7. But you can see we have to allocate this further reduction of 50% for the live load. So because of that reason, you will end up with 0.525. So can you understand, have you used this live load reduction earlier in any coursework or any assignment? Have you used this live load reduction? Right. So I'll try and I'll show you that the place where you can find this reduction. So you have to allow for some reduction, and then when it comes to wind load, you have to use 1.5 times the wind load. So that is combination 2, where we said we'll have this QK reduced by multiplied by 0.7. So 1.5 into 0.7, 1.05, and then we allocate only 50% of that to allow for live load reduction. So then similarly, you have to consider the wind load in the minus X direction. Then we can look at combination 3. So here you get dead weight 1.35 and live load. Now this combination is 1.35 GK plus 1.5 QK plus 1.5 into phi 1 times wind, whereas for the wind phi 1 value is 0.5. So 1.5 into 0.5 is 0.75. So here you get 0.75, and slab live also you get 0.75. So this way, you can see that is the load combination 3 that we discussed. Okay. And so here you can see we have got 3 combinations, and one is this one 1.0 GK, 1.5 WK. This one we said it's not very critical. This one 1.35 GK, 1.5 WK, and 1.5 into 0.7 times QK, 1.05 QK, but we consider only 50% of that. So that's why you get 0.525 QK. And then we also have this combination where you get GK, QK, 1.35 GK and 1.5 QK. But when it comes to WK, you are multiplied by 0.5. When it comes to WK, you are multiplied by 0.5. So you get 0.75 here. And this one also we have to consider half the value because we can allow a 50% reduction for the QK. So here also you get 0.75, here also you get 0.75, and that's what you have seen. And in addition to that, we will consider 1.35 GK plus 1.5 QK. And that case will not be critical because you can clearly see this case is more critical than this one. The reason is, here you get 1.35, here you get 0.75 QK, 0.75 QK, but there's an additional load here. And we apply this load in both direction, X direction and minus X direction. So because of that reason, when you consider the envelope, you will find that this particular case will not be governing. But still, we consider this because that gives, sometimes we like to see the effect of dead and live loads only. So because of that, we create this combination as well. So when you're looking at the results, sometimes you might like to look at it. So because of that reason, we make use of that particular combination. So when you look at all the load combinations, so you get all those combinations, 3x, you get 0.75, 0.75 as I have just explained for live load and the wind load for combination 3. And then what we can do is we can actually define an envelope only in X direction. So only the X loads plus the vertical load combination 4 will be there. And here we are going for the envelope. No addition, no linear add. We are going for the envelope. And here the scale factor is 1. Similarly, you can also look at all the load cases in Y direction. And then we can also see the envelope. We can also see the envelope, and that is the envelope in X direction and envelope in Y direction. So that way we can actually create all the necessary combinations, and we can get the results for in a particular direction by using NVX and NVY. And if you want the overall effect, you can consider this final case, which is envelope XY, envelope XY. So then comes the situation where we need design the foundations, and foundations can be designed using the prescribed strengths and the actual service loads. So to determine the actual service loads, here you can see we'll have to define this first load case, that is 1.0 GK plus 1.0 WK. So dead wind, but under service conditions. So similarly, you can create all the service conditions like this, and it can so you can see under service combination 3, here you get the third one that we were discussing. This wind load is reduced by 50%. That is 1.0 wind is reduced by 50%, that is 0.5. And live load is also, we consider 50% of the live load. So you get 0.5 and 0.5. And in ultimate case, we got 0.75 and 0.75. Here under service conditions, you get 0.5 and 0.5. So we have defined all the service combinations, and service combinations, this needs a small adjustment here. So it should be service ENV XY, service envelope XY, like this one. Okay. So you have to define load combinations for service conditions and ultimate conditions separately, because for the foundation design, sometimes we can make use of these values, the service values, to design the foundations. So we have to define service combinations and ultimate combinations. And once you define all that, the model is reasonably ready for generating the other flows. But before we do that, we have to see whether we are going to use the same column size throughout the height of the building. So here I'm going to consider something like 30 floors for the building. Floor to floor height is 3.6 meters. So we can get an idea about the complete building, and also we can see what are the important parameters we will have to perform calculations. So you get these values, and I'll save it, and then we'll open V1. Then the other important thing is, whether you are going to use the same column size throughout the height of the building. So generally, in the ground level of a 30-story building, you might end up with something like 1200 by 1200 columns, or it can be even 1300 by 1300, or it could be even elongated with something like 2 meters of length and 0.35 meters of thickness, or 0.4 meters of thickness. So they can be either elongated columns or square columns. And so the important thing to see is, are we going to use the same column size throughout the 30 floors, or are we going to reduce the column size when the column loads are lower? So in the upper part of the structure, the column loads can be lower. So what you can do is, you can make a copy and replicate this at this particular level. And then what you can do is, you can select all the columns in one stroke. Now all the columns are selected, so as the shear walls. But when you assign the properties, like column 800 by 800, these shear walls nothing will happen to the shear walls, because they are not defined as a column. So only the columns are allocated. So this way you can see I have changed the column size from 1000 to 800. And then you can generate the model, so that in the upper part of the building you get 800 by 800 columns. In the lower part of the building you get 1000 by 1000 columns. So any questions so far from what we have discussed? And how about this live load reduction? Have you used this live load reduction earlier? Can somebody give an answer? Janit?
No, sir, we haven't used, I think.
All right, then I'll show where to get it. Okay.
Hello, sir.
Yeah, then I'll show you in the after the After the break, right? So we'll take 10 minutes break. I'll start around 2:20. Okay. I'll start
Okay, sir.
around 2:20, and I'll show you this, where to find these loads in the national annexure of UK, so that you can use this live load reduction, and you can see how the factor of safeties can be reduced to take account of these take account of the fact that all the live loads cannot act simultaneously at full value, because the live load factors, live load values that have been recommended include and include about 100% allowance for dynamic loads. So that means 50% is the actual load. The remaining 50% is what is allocated for dynamic effects. But these dynamic effects are local effects. So when you are looking at that full structure, we don't have to consider these local effects. So because of that reason, the codes allow us to have a reduction of about 50% depending on the number of flows. The maximum reduction is 50%. Okay, with that I will stop, and because I want to convert this recording, shall I end the session and